This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 9 of Week 3. Radiation. The Stefan-Boltzmann law tying emitted power to absolute temperature. Emissivity and absorptivity, bringing real bodies below the ideal black body. The view factor for geometry. And the two-surface gray body enclosure formula, tying them together. Radiation is the third mode. Conduction and convection need matter. Radiation does not. It travels as electromagnetic waves, even across a vacuum. Two features set it apart. First, no medium needed. The sun heats the earth across empty space. Second, it scales as the fourth power of absolute temperature. Double the absolute temperature, and emitted power jumps 16-fold. That's why radiation dominates at high temperature. Furnaces, combustors, glowing surfaces, and is often negligible near room temperature. Start with the ideal. A black body absorbs all incident radiation and emits the maximum for its temperature. Following the Stefan-Boltzmann law, EB equals sigma T to the fourth, the radiated power per unit area. Sigma is the Stefan-Boltzmann constant. T is the absolute temperature, Kelvin or degrees Rankine. Never Celsius, never Fahrenheit. Total power off an area A is sigma A T to the fourth. And remember, black body is a thermal idealization, not a color. Matte black paint and ordinary masonry are both near it. This is the rule that decides most radiation problems. Every radiation formula uses the fourth power of temperature, so the 0 point matters. A temperature difference is fine in either scale, but T to the fourth is not. Convert first. Kelvin equals Celsius plus 273.15. Rankine equals Fahrenheit plus 459.67. Then raise to the fourth, and T1 to the fourth minus T2 to the fourth is a difference of fourth powers. You can't factor the conversion out of it. Sanity number. 27 Celsius is 300 Kelvin. Using 27 to the fourth is off by roughly 15,000. Write Kelvin or Rankine beside every temperature the instant you read a radiation problem. Real surfaces emit and absorb less than a black body. Three properties describe incident energy and always sum to one. Absorptivity alpha plus reflectivity rho plus transmissivity tau equals 1. The fractions absorbed, reflected, and transmitted. And emissivity epsilon is how well the surface emits, as a fraction of the black body. Real emissive power is epsilon sigma T to the fourth. For an opaque body, tau is 0, so alpha plus rho equals 1. The emissivity table lists typical values. Polished metals low. Masonry and paint near 0.9. Tracking emissivity and absorptivity as separate, wavelength-dependent numbers is too much for an exam. The gray body model collapses it to one property, alpha equals epsilon, between 0 and 1, constant with wavelength. For an opaque gray surface, epsilon plus rho equals 1. The black body is the limiting case, alpha equals epsilon equals 1. Unless a problem says otherwise, assume gray. That single assumption lets us write one closed-form enclosure equation from just the surface emissivities. Now geometry enters. The view factor, also the shape or configuration factor, F12, is the fraction of radiation leaving surface 1 intercepted by surface 2. Pure geometry, no temperature. Two rules find the ones you need. Reciprocity. A1 times F12 equals A2 times F21, flips a view factor between two surfaces using their areas. Summation. The view factors from any surface to all in the enclosure sum to 1. Each is between 0 and 1, and a flat or convex surface can't see itself, so its self-view factor is 0. Key special case. A small convex object in a large enclosure sees only the enclosure, so its view factor is exactly 1. Now the centerpiece. For two diffuse gray surfaces forming an enclosure, the net exchange is a single potential difference. Sigma times T1 to the fourth minus T2 to the fourth, across three resistances in series. The surface resistance at surface 1, the penalty for being non-black. The space or geometric resistance, the penalty for not fully facing each other, and the surface resistance at surface 2. It's an exact electrical analogy. Emissive power sigma T to the fourth is the voltage, Q12 the current, the three terms resistors in series. This diagram is exactly that resistor chain. Set both emissivities to 1 and the surface resistances vanish, leaving the two black body result, A1 F12 sigma times the difference of fourth powers. Same series resistance bookkeeping as the conduction networks, only the resistor definitions change. The handbook tabulates 4 standard two-surface enclosures, all with view factor 1. Large parallel planes, equal areas. Long concentric cylinders, area ratio is the radius ratio. Concentric spheres, the radius ratio squared. And the small convex object in a large cavity, area ratio goes to 0. The cavity's surface resistance vanishes. Only the small object's emissivity survives, collapsing to epsilon sigma A times surface temperature to the fourth minus surroundings to the fourth. That's the small and large result, the worked problem coming up. The general formula needs the two temperatures in Kelvin, the two emissivities and areas, the view factor, and the Stefan-Boltzmann constant. Worked problem. A small oxidized steel plate hangs in a large room, 0.3 by 0.4 meters, radiating from both faces. Its surface is held at 250 Celsius, the room walls at 25. Emissivity is 0.58, oxidized steel from the handbook table. The plate is tiny compared with the room. Find the net radiation heat loss, both faces. The plate is small and convex inside a large cavity, so the view factor is 1, and the surrounding surface resistance vanishes. The small and large limit applies. Q dot equals epsilon times sigma times A times the difference between the plate's surface temperature to the fourth power and the surrounding surface temperature to the fourth power. Convert to absolute temperature first. 250 Celsius is 523 Kelvin. 25 is 298 Kelvin. The area, doubled for both faces, is 0.24 square meters. Take each fourth power separately before subtracting. Substitute and multiply through. Q dot is about 528 watts. 4 checks. Units resolve to watts. Sigma's Kelvin to the fourth cancels that from the temperatures. Magnitude, 530 watts off a quarter square meter of hot steel is sensible for a strong radiator. Dominant term. The surface to the fourth is roughly 9 times the surroundings to the fourth, so the hot plate sets the loss. Sign, surface hotter, so Q dot is positive. A net loss from the plate, as drawn. 5 traps that quietly cost points. 1. Celsius or Fahrenheit in T to the fourth. Stefan-Boltzmann needs absolute temperature. Convert to Kelvin or Rankine before the fourth power. The number 1 trap. 2. Factoring the difference of fourth powers as a fourth power of the difference. It's T1 to the fourth minus T2 to the fourth, not T1 minus T2 all to the fourth. Compute each separately, then subtract. 3. Dropping a radiating face or wrong area. Both faces doubles the area. A flush-mounted plate radiates from 1. 4. Forcing the full enclosure formula when small and large applies. A tiny surface in a large cavity has view factor 1, and the rate is just epsilon sigma A times the difference of fourth powers. 5. Confusing emissivity with absorptivity, or assuming it's 1. Real surfaces are gray, emissivity below 1. Only a black body has emissivity 1. Bookmark the pages. Radiation opens with Stefan-Boltzmann, the types of bodies, and alpha plus rho plus tau equals 1. Then the emissivity table, view factor reciprocity and summation, the small and large result, the 2 black body result, and the 2 gray surface enclosure formula with its special case table. All of radiation lives on 4 facing pages. Fold the corners and write absolute T in the margin. Radiation complete. You now have all 3 heat transfer modes: conduction, convection, and now radiation with Stefan-Boltzmann and the gray body enclosure. The takeaways: emitted power scales as the fourth power of absolute temperature. Real surfaces are gray, and emissivity equal to absorptivity, with alpha plus rho plus tau equals 1. Geometry rides in the view factor, and the 2 surface gray enclosure is 3 resistances in series, collapsing in the small and large limit to epsilon sigma A times the difference of fourth powers. Next comes combined mode analysis, folding the radiation and convection losses off one surface into a single network through a radiation heat transfer coefficient.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.